Today's seminar on theoretical modeling of infrared thermography is presented by Dr. Volkmar Nolting. I'll just briefly introduce you the speaker. Dr. Volkmar Nolting studied towards his MSc at the University of Münster in Germany, and his PhD at UNISA. And his research fields include electromagnetic methods in NDT, theoretical solid-state physics, many body physics, magnetism, and phase transitions. His work experience includes his current position as a senior lecturer at the Vaal University of Technology, and had held previous positions at the Department of Physics in Medunsa as a senior lecturer and various other positions. His recent publications include magnetic 4F systems and their applications in spintronics, collective electronic excitations in ferromagnetic metals, theoretical modeling of high energy alloys, among others. That being said, I will now give the floor to Dr. Nolting to give his presentation for the day. Thank you.
Okay, thank you, Chair, for this invitation and for this opportunity to present my work on theoretical modeling of thermal radiation. As you already mentioned in your introduction, I'm working at the Vaal University of Technology in the Department of Mathematics, Non-Destructive Testing, and Physics. Any object radiates infrared energy. This radiated energy increases with temperature, and this temperature dependence is described by two very famous laws of physics, which are well known even outside the physics community. And that is, first of all, Planck's law, and then Stefan Boltzmann's law. According to these laws, the energy density of the photon gas is described by this integral over the spectral energy density. So epsilon omega of omega and t is the spectral energy density. So that is the energy per unit volume, per unit frequency, and that is integrated over all frequencies omega. The analytical expression for the spectral energy density that was first given by Planck in the year 1900, and it contained for the first time the idea of quantization of electromagnetic radiation. And that was well before the introduction of quantum mechanics, which makes Planck's idea even more remarkable. And if one integrates the spectral energy density over all frequencies omega, then one obtains, and one can do this either analytically or numerically, then one obtains that this energy density is proportional to T to the power 4, where T is the absolute temperature measured in Kelvin, and sigma is the Stefan Boltzmann's constant. The intensity received from the surface of a perfect black body at room temperature is then, according to Stefan Boltzmann's law, equal to 448 watt per square meter. Now, how the spectral energy density behaves as a function of frequency omega and temperature T, that is shown on the next slide. Yes, that is here. This is the spectral energy density as a function of wavelength lambda, plotted for 3 different temperatures T. And what is interesting here is that the maximum of the spectral energy density moves with increasing temperatures to lower wavelength. And that is the result for Wien's displacement law, says that lambda max times T is equal to a constant value. which is given here in meters times Kelvin. And lambda max lies then for most temperatures in the infrared part of the electromagnetic spectrum. Only at very high temperatures above 3870 Kelvin, this maximum moves then into the region of visible light. And that is why we can see, for example, a piece of red iron glow. Yeah, that concludes the introductory part of this presentation. Then if we can see on the next slide, we have the table of contents. So we've already seen that thermal radiation is part of the electromagnetic spectrum. The corresponding quasi-particles are the photons, and therefore the theory part describes the theory of the photon gas. Photons behave according to the Bose Einstein statistics. So there are quantum particles which behave differently compared to classical particles, and that will be discussed in the theory part of this presentation. Then in the results section, we will look at PV isotherms of the photon gas and compare that with corresponding results for a classical gas. A classical gas would, for example, be a gas of oxygen molecules or a gas of nitrogen molecules. And this photon gas behaves completely different compared to that classical gas. We will also look at the entropy function S as a function of T. This entropy is discontinuous at the point of the phase transition. The phase transition is a phase transition from the liquid phase to the vapor phase, and that is as a result of Bose Einstein condensation. We will also look at the heat capacity as a function of temperature T and confirm that phase transition is a phase transition of a first order. However, we will see that this phase transition also depends on the dimension d of the system. Then finally, in the application part of the presentation, we will look at the application on thermographics. That means we will look at thermography as a non-destructive evaluation tool, which is an application that is used in our department to look at and to find out discontinuities in solid materials. So the theory of electromagnetic radiation is the theory of the photon gas, where the radiation field is described by this homogeneous wave equation, where the delta is the Laplace operator. So that is d squared over dx squared plus d squared over dy squared plus d squared over dz squared. So that part describes the space dependence of the wave function psi of r and t, whereas d squared over dt squared describes the time dependence. C is the wave speed, which is in this case equal to the speed of light in vacuum, which is equal to 3 × 10⁸ meters per second. So psi, the wave function, is a function of r and t, and solutions are of this form, where k is the wave vector, and e to the ikr describes a plane wave. Now, if we insert the solution into the wave equation, then we obtain an equation of motion of this type. And this is the equation of motion of a harmonic oscillator with the k-dependent frequencies. Next slide, please. With the k-dependent frequencies omega of k is equal to c times k. Yes, where k is the wave vector. Such k-dependent frequencies are in physics known as dispersion. A result of that is that the energy eigenvalues become discrete and quantized, where n can go from 0 up to infinity. That means that each photon then has an energy E is equal to h bar ck, where h bar is Planck's constant. It has the momentum P is equal to h bar k. The rest mass m naught is equal to 0. That means photons have no rest mass. They have a spin s is equal to 1, which characterizes photons as bosons, and then a chemical potential mu is equal to 0. That is a consequence of the fact that the particle number n for photons is temperature dependent. The next slide. Yes, the density of states, thank you, of the photon gas, that is calculated from the phase space volume, and the density of states comes out as proportional to E squared. And from this density of states, we can then calculate the average number of photons at a temperature T in equilibrium. That is calculated from this integral over all energies E, where rho of E is the density of states, and F plus of E and T is the Bose Einstein distribution function, which describes the statistics of the photon gas. Please note that this particle number is temperature dependent. And what consequences this has now, according to with regards to the occupation number of the lowest possible energy state, we can see on the next slide. So here we have the occupation number of the lowest possible energy level and the results for bosons. So for example, photons is compared with corresponding corresponding values for fermions. So for example, electrons. So in the case of electrons, the lowest possible energy level E is smaller than the chemical potential. Therefore, e to the power beta, E minus mu, is a very small number, which goes for T approaching 0, goes towards 0, and therefore the occupation number for fermions approaches 1 at very low temperatures. On the other hand, for bosons, e to the power minus beta mu is approximately equal to 1 minus beta mu at very low temperatures. So that means the occupation number for bosons approaches infinity. That means the occupation number can take on arbitrarily large values. Furthermore, in the condensed phase, the boson condenses in the lowest energy level, so that n naught over n, so that means the number of photons in the lowest possible energy state divided by the total number of photons is temperature dependence, and this is described by this last equation on this slide. And if one plots this as a function of T, one obtains a phase transition from the vapor phase into the liquid state, and the condensed phase describes then Bose Einstein condensation. That means that is the condensed phase from the liquid phase into the vapor phase. And what kind of phase transition that is, we will see later on during this presentation. So then on the next slide, yes, we see the number of photons of frequency omega as a function of temperature T, and we compare those results with corresponding occupation numbers for a classical gas. Now, at the occupation number for photons first starts at 0, at T is equal to 0, and then the occupation number slowly increases as a function of temperature, whereas for high temperatures, the occupation number practically linearly increases with temperature T and can then take on very large values for high temperatures. On the other hand, for the case of the classical gas, the occupation number also first starts at 0, at T is equal to 0. So it means the two curves are very similar at low temperatures. However, at higher temperatures, the classical gas approaches 1 at very high temperatures. That means the classical gas, especially at high temperatures, behaves very much different to those of the photon gas. Now, interesting is also the following comparison. The temperature where the photon gas reaches atmospheric pressure is calculated from this formula. And if we insert for P the pressure, atmospheric pressure, then we obtain a very high temperature of 141,000 Kelvin. At this temperature, the photon gas has a particle density of the order of 10 to the power 22 particles per cubic meter. If we compare this with the particle density of an ideal gas at the same pressure and room temperature, then we obtain a particle density of 10 to the power 25 particles per cubic meter. And again, these differences are due to the different statistics for the photon gas on the one hand and the classical gas on the other hand. Now we come to the results section of this presentation. At high particle densities and low temperatures, the ideal photon gas shows huge differences compared to the ideal classical gas. In particular, in the region of condensation, the pressure is independent of volume V. And the critical pressure for condensation to take place, that decreases with increasing volume V according to this formula. And that is now shown on the next slide, where we see the critical pressure as a function of volume V. And then together with this critical pressure, we have two isotherms of the photon gas for two different temperatures T. Now, on the right-hand side of the critical pressure, we are in the vapor phase. On the left-hand side, we are in the condensed phase. And you see the isotherms are independent of volume V in the condensed phase. So there, the pressure does not depend on volume V. We have here straight lines parallel to the axis. And then only in the vapor phase, the pressure decreases with volume V and finally reaches 0 for infinitely large volumes V. These isotherms for the photon gas are to a large extent similar to corresponding isotherms for a classical gas. That is shown in the next slide, where we have isotherms for a classical gas. And these isotherms there are three different regions. To the left-hand side, we are in the liquid phase. On the right-hand side, we are in the vapor phase. And in between, where we are in the condensed phase, where the liquid changes phase to vapor. And in particular, the condensed phase and the vapor phase are very similar to the corresponding isotherms of a photon gas. We see the pressure being independent of volume V in the condensed phase, and then pressure decreasing with volume V in the vapor phase. The decisive difference is that for a classical gas, we have to introduce interactions between the molecules for phase transitions to occur, or for an ideal classical gas where there are no interactions taking place between the molecules, there are no phase transitions, whereas in the case of the photon gas, phase transitions occur even if no interactions between the photons are considered. So that is the decisive difference between the classical gas and the photon gas. So yes, here we've plotted the entropy function S as a function of T. And this entropy function is discontinuous at T is equal to Tc, where Tc describes the phase transition from the vapor phase to the condensed phase. the entropy function S of t increases with t to the power 3/2 in the condensed phase, and it increases with ln of t in the vapor phase. And from the discontinuity at t is equal to Tc, we can read of the heat which is released during the phase transition. That is further explained on the next slide. Yes, the heat delta Q is calculated from that given formula, where g of z is a polynomial in z, and it turns out that the denominator is finite at z is equal to 1, which means that a definite amount of heat is released during the phase transition, which means that the phase transition is of first order as long as the system is three-dimensional. On the other hand, for the one- and two-dimensional system, the corresponding expression in the denominator diverges, so that delta Q is equal to 0, which means that in the one- and two-dimensional system, the phase transition is of second order. That means the phase transition depends on the dimension d of the system, and such dependencies have also been observed in other systems, in other physical systems, for example, in magnetic systems. That is further explained on the next slide. Yes, if you, for example, think of the Heisenberg model and the Ising model, there the phase transition depends also on the dimension d of the system. And that is an interesting story, because Ising himself in the year 1920 had to solve the one-dimensional model. And this one-dimensional model and also the two-dimensional model can be solved exactly. So there are no approximations involved in these results. And to the great disappointment of Ising's supervisor, Ising could show that the one-dimensional model does not show a phase transition between ferromagnetism and paramagnetism. And furthermore, Ising could not solve the two-dimensional model. The corresponding solution was only presented very much later by Onsager in the year 1944, and he could calculate an expression for the Curie temperature Tc of the model, which is of course dependent on the interaction between the magnetic moments. So the two-dimensional model does show a phase transition from ferromagnetism to paramagnetism, and important for the observation of phase transitions is first of all the thermodynamic limit. That means one has to consider an infinitely large system. One can show again exactly that finite systems do not show phase transitions. Important is also the range of the particle interactions, because the larger that range is, the more likely phase transitions occur. And then, like we saw in the example of the Ising model, the dimension d of the system can also become important. Yes, according to statistical mechanics, the phase transition is the result of a limiting process. That is why one has to consider the system in the thermodynamic limit. For finite systems, there are no phase transitions. So, for example, if one has an ideal classical gas or a classical gas, then the pressure P as a function of V shows a first order phase transition. And while the system changes phase from liquid to vapor, the pressure stays constant as a function of volume V, like we saw in the earlier slide where we had the phase transition for a classical ideal gas from liquid to vapor. Those of you in the audience who have worked on phase transitions will know that phase transitions in very small systems have been reported. However, the theoretical description of such phase transitions is a very challenging subject. First of all, because of the non-equilibrium situations in such finite open systems. Finite systems are not in equilibrium. Also, important is the dependence on the final results on the boundary conditions, and finally the statistical ensembles. That means the microcanonical ensemble, the canonical ensemble, and the grand canonical ensemble do not deliver equivalent results for finite systems. And next slide, please. Yes, we also looked at the heat capacity as a function of temperature T, and that heat capacity shows a peak at T is equal to Tc, which again characterizes the phase transition as one of first order. Interesting here is also that lambda shape of that peak, which is a result of Bose Einstein condensation. Yes, and then in the last slide, we look at yes, applications of thermal radiation. And here in particular interesting is thermography as a non-destructive inspection technique. So here one uses the fact that different materials show different thermal patterns when submitted to heat. So if the specimen and the flow, the discontinuity, are made up of different materials, then that should show up in their thermal pattern and should be made visible with an infrared camera. In the case of superfluid helium-4, one can calculate the heat released during condensation, and that comes out from a theoretical calculation as 0.347 milli-electron volt, and it would be interesting to compare that with corresponding experimental values. You can see here that the transition temperature is normally very low, only a very few degrees Kelvin. However, in the case of magnetic system, Bose Einstein condensation of magnons has been observed at room temperature, and from these observations, the phase transition should be able to be observed much more easily, and more interesting results can be expected from such experiments. Yes, I thank you for your patience and for your attendance, and I thank you for the invitation and for that opportunity to present my results in your seminar. And if there are any questions, you can direct them now during that question and answer session. Thank you very much.
Yeah. If there are any questions, please either type them on the chat platform. I hope the chat platform is now enabled. Or you can also just raise your hands, and then I will give you the opportunity to ask. May I ask if this thermographic application is already something is it in the medical industry mostly applicable, or what's
Yeah, so I think that can also be applied, I think, but we use it to detect flaws in materials. Yes, we have the equipment in our lab, and yeah.
Any medical applications that you know?
I'm not so sure about that, but I can certainly read this up whether there are applications of that type.
Right. And what does this have to do with that photon statistics that you showed us earlier? Is it like saying the the photon statistics that you showed us earlier, the Bose Einstein condensation and all?
Yeah, so thermal radiation is, of course, part of the electromagnetic spectrum, and the photons are the particles of that radiation, of thermal radiation. So the statistics is the statistics of the particle that provide that sort of radiation.
Right. Very
Maybe
interesting.
I can come in quickly. There are definite applications of thermography within the medical field. the non-destructive testing that Dr. Nolting is talking about actually lends quite a lot of their own inspections and testing techniques through the medical applications. Thank you, Chair.
I see. Thanks for that, Ike. So, Dr. Nolting, this thermographic research at Valley University, is it like a research group, or is it something that you?
Yes, we have a non-destructive testing research group. Yes, and we use different techniques to detect flaws in materials, and this thermography is one of the tools that we use. Yes, we have the corresponding equipment available, and I'm also trying to yes, first of all write this up, this current presentation, and then also collaborate with some of my colleagues also to do some work in thermography in the future. Oh, okay. No, thank you, and I also thank you for that opportunity to present in your seminar.
It was a pleasure.
Thank you.